chapter 3 that we need to talk about is energy and temperature. So we've already kind of talked about this. We're just going to be just a little bit more specific and more in detail. So temperature, again, is the measure of the thermal energy in a substance. So temperature is going to be the measure of it. So it's an amount of thermal energy in a substance. So again, thermal energy is associated with that random motion of particles. So when you see that there's a ton of random motion in particles, it's going to have a high amount of thermal energy. If we see low amount of motion in the particles, it's going to be low thermal energy. So high temperature, high motion, low temperature, low motion. So in that case, we think about the particles are always wiggling, right? Like even when we have a solid, our particles are still wiggling in the solid. So we call that motion Brownian motion. So I think it's kind of a cool word. I like that term a lot. So that describes the fact that particles are always constantly wiggling around. However, there is one temperature where they stop wiggling around. That value is called absolute zero. So when we are talking about absolute zero, that occurs at 0 Kelvin. We'll look at our temperature scales more in detail in just a second here, but particles are always wiggling around unless the temperature is 0 K. So we call this absolute zero because the particles are no longer moving. We've measured this and we figure out it occurs at minus 273.15 degrees Celsius. So that's how we set the Kelvin scale up. So we said, okay, absolute zero, we're going to call minus 273.15 degrees Celsius, zero, and then we just add 273 from there to get to the Celsius number. So, or to get Kelvin to Celsius. So. That's kind of the idea there. That's why when we look at the conversion, it's got this funny number is because that's actually the Celsius value at absolute zero. And then when we talk about heat, so we've got temperature and we've got heat. Sometimes in those, like in our everyday lives, those might be the same, but in chemistry, those are going to be different. So if we have temperature is the measure of the thermal energy, heat talks about the transfer of thermal energy. So we talked about endothermic and exothermic reactions where we're talking about energy going in and out of the reaction system to the surroundings. So heat would be what we're talking about when we're talking about transferring those, transferring that energy back and forth. So again, temperature is the measure, heat is the transfer. Sorry about that. So the temperature scales here, we work with 3 different temperature scales. We've talked about them just a little bit, but to be more clear, they're Fahrenheit, Celsius, and Kelvin. So Fahrenheit's what we usually deal with. Again, Celsius is the metric measure, and Kelvin is the SI unit. So when we look at our picture over here, what this is showing us is all the different places that different things occur on the scale. So up here, water boils at 200 degrees or 212 degrees Fahrenheit. It boils at 100 degrees Celsius, and it boils at 373.15 Kelvin. So that's kind of the idea there to show you the distance between the freezing and boiling point. We can see that Fahrenheit has more individual divisions, whereas Celsius has bigger gaps because it only has 100 in between versus 180 degrees in between. And then where water freezes is at 0 Celsius, 32 degrees Fahrenheit, and then 273.15 K. And then here are your conversions down here at the bottom for absolute to zero. So what this is just trying to show you is how different each of those scales are. And we'll do some practice conversions next as well. Okay, so this is just a visual representation of those same conversions. So here, if we want to go from Fahrenheit to Celsius, we could use this equation. The drawings kind of flip for these two. So if we want to go from Celsius to Kelvin, we want to get Kelvin from Celsius, we would use this equation. And if we want to get Kelvin from Celsius, we would use this equation. So I'm going to go ahead and stop here, and we will work through some temperature conversion examples. Okay, hello everyone. We're going to go ahead and do some temperature conversion examples. So I apologize if it's a little loud. I'm in the lab and I have the research on, so hope it's not too distracting. All right, so our first example in the notes says we're going to convert 70.0 degrees Fahrenheit to degrees Celsius. So the first thing we got to do is we got to find an equation that relates these two together. It's kind of complicated to go back and forth between degrees Celsius and degrees Fahrenheit versus going back and forth between degrees Kelvin and Kelvin and degrees Celsius. It's not degrees Kelvin, it's just Kelvin. So we've got 70.0 degrees Fahrenheit, 2 degrees C. We have an equation that relates those two together. So we have degrees Celsius equals Fahrenheit minus 32, all divided by 1.8. So from here, we're just going to figure out what we've got and what we need. So we have the info that we're given is we start at 70.0 degrees Fahrenheit. And where are we going? We're looking for degrees Celsius. So there we go. I'm going to go ahead and therefore just plug straight into my equation. So if I have degrees Celsius equals Fahrenheit, I'm just going to write 70.0. I know I harp on you guys about units. It just gets a little weird with these temperature conversions because in the end, our answer will be degrees Celsius. We won't have Fahrenheit or anything anywhere in our answers. So if I go ahead and I get my calculator and I type this guy in, I have 70 minus 32, and then I'm going to divide that by 1.8. So in my calculator, I have my degrees Celsius is 21.111111 forever. So I have to go back and I have to determine my amount of significant figures. So in this case, when I add and subtract here, neither of these numbers are going to affect my number of significant figures, so I'm still going to have one number after the decimal place. Then I would have 3 significant figures in division, so I'm going to take 3 significant figures in my answer, 21.1 degrees Celsius. So 70 degrees Fahrenheit, you might think that's pretty stinking close to room temperature. Well, room temperature in Celsius is about 21.1 degrees Celsius. So we're going to go ahead and do the other 2 examples as well. Okay, so I've gone ahead, I've erased my whiteboard here. Let me just get you a better angle. So I've gone ahead, I've erased my whiteboard, I've set up example 2 in the notes. So this says 345.783 degrees Celsius, and we want to convert that to Kelvin. So let's figure out what information we're given, what's our starting point, what's our end point, and then we'll go look for any tools we need. So if we have 345.783, this is the most specific piece of information we're given. So we'll go ahead and use that as information. In the end, we're looking to get to Kelvin. And then I'll probably need something, if I'm looking for unit conversion, I need to find something that relates my Kelvin and my Celsius. So in that case, I have an equation that says Kelvin equals degrees Celsius plus 273.15. Okay, so pretty straightforward. We've got degrees C. We have that piece of information. We're looking for Kelvin. Let's go ahead and plug on in. So K equals degrees C, 345.783 plus 273.15. My answer is, let me grab my trusty calculator here, 345.783 plus 273.15 is, in my calculator, 618.933, and that's Kelvin. So again, when we're talking about Kelvin, we never use a degrees Kelvin, it's just K. So I would say 618.933 K is how I might say that. So if I'm looking for my significant figures, this is the only thing affecting my significant figures. This is not affecting it, so I round my answer to the same number of significant figures. This is considered an exact number. So in the end, we have 618.933 Kelvin. Okay, so last temperature conversion example here. We have 647 Kelvin, and we're going to take that to degrees Celsius. So let's figure out what we're given, what's our starting point. So the information we're given is we have 674 K. Our end point is going to be degrees Celsius. So if we get to degrees Celsius in the end, we've gotten where we're going. And then when we're comparing these two values, we can look for an equation, some sort of unit conversion factor. Again, in this case, it's an equation that relates the two. So we can say that degrees Celsius is K minus 273.15. Okay? So pretty easy here. I've got degrees C, I've got K. I'm given K, I'm looking for degrees C. Sounds like I'm in the right place. So degrees C is 674 minus 273.15. And then from here, we have our math to be done, which is 674 minus 273.15. The answer we get is 400.85 degrees Celsius. However, we have to make sure that we have the correct number of significant figures. So if I look up here at my answer, I only have 3 sig figs, as well as the fact I've got no decimal points. So if I round this with no decimal points, I've got 3 sig figs, so it kind of fits both. So if I have degrees Celsius, in the end, with proper significant figures, my 8 makes my 0 round up. So 8 makes 0 go to 1, so I would have 401 degrees Celsius with proper significant figures.